chair there. Let's say right now, relative to the amount of space available, is it saturated? Is this room saturated? Can it still allow more people to walk in and take up the places? There is plenty of empty space, right? Now what will happen when all these seats are full? Every chair, there's a person sitting on every chair. What would you call that room? Will you call that room saturated? That's where room will get saturated. You won't, if one more person walks in, they won't have a space to sit. And the rule will be they cannot stand. And they cannot sit on the floor. They cannot sit on table. What are those rules? These are the rules set by nature. So if one person walks in, imagine the entire room is full. If one person walks in and the person is sitting there and everywhere and wants to sit there, force the person and pushes that person away. And the next one, and the next one. Someone from there has to leave. Right? So if you try to force water molecules into the air, where the air is already full of moisture, doesn't have any more room to hold the moisture. If you forcefully add moisture into the air, so from somewhere around, some of the moisture which was already there will condense into a droplet and fall out of the air to make the room for new droplets to walk in. Now, if the entire room was empty, let's say at the beginning of this class there was no one, the whole room was empty, what will be relative humidity or relative capacity of this room for humans? It's 0%. Is it? So relative to the number of chairs in there, how many chairs are filled? 0. So let's say if there were 100 chairs in this room, let's assume there were 100 chairs in this room, and there was no one sitting on those chairs. They were empty. Relative will be 0. If there was one person sitting on one chair, what will be the relative humidity? 1%. If 10 chairs are filled, 10%. 50 chairs are filled, 50%. 99 chairs are filled, 99%. That's where only one person more can be added. Once all chairs, 100 chairs are filled, it's 100% relative humidity. So you cannot add. Similar fashion. Now, let me extend that analogy from this chairs and the room to actual air, because this chair and the room, we cannot really physically change the volume of the tables or chairs. But imagine now these air particles. So air being mainly nitrogen, oxygen. Let's forget trace gases, they might be there. But let's say there are these two molecules of air. There might be two oxygen molecules, nitrogen, or one oxygen, one nitrogen. At present, in this room, let's say they are, on average, they are separated by that much distance. I'm just zooming in, like showing you what it might look like, okay? So there are two particles, that's that far apart. Now if you start heating up the air, if you start increasing the temperature of the air, what will happen to this average gap between the particles? Will it decrease or increase? By temperature, by heating it up. I want answer from everyone. Yes. You're heating the air. It should increase, not decrease. Okay? You're increasing the temperature, they go further, because imagine you're heating up anything, it expands, right? So imagine you fill air inside a balloon. You heat up the air in the balloon starts going up. On a very hot summer day, if your car tires have been filled to max on a cold winter day, and now you're driving on a hot summer day, the pressure inside the tires can be higher. They won't blow up a lot because they are steel reinforced tires. The modern tires are steel reinforced, so the volume is almost constant, but the pressure goes high because they're trying to expand, molecules are trying to expand and they can't. So let's come back. For a given temperature, that distance is set. A mean or average distance is set. And basically what's in between them? What's in between those two particles? Perfect vacuum in air, right? if those fists were particles, air particles, air molecules. There's no air molecule in between. There's the average distance between two molecules. It's empty, and that's where one water molecule can jump in. Okay. Now, if you start heating up the air, and again there's a rule. There will be some natural rule that you cannot add two water molecules in between two oxygen or nitrogen molecules at a given temperature, because there's a minimum gap between water molecule and oxygen molecule that must always be there because of intermolecular forces. Now, if you start heating up that air, what's going to happen? These air molecules are going apart. Now, there's more distance in between them. Can you add more water molecules inside? You can. Now, further you can. So, the amount of water molecules that can be added in the air are relative to also the temperature of the air. If air is at higher temperature, you can add more water molecules. With a low temperature, you add less water molecules. So relative humidity is the ratio of amount of water molecules which are present in the air at a given condition divided by the maximum possible amount of water molecules that could be added to that air at that given condition. Clear? Is that clear? So, relative humidity is 100%, air is said to be saturated. Okay? If the entire air is, all the empty spaces are filled, it's saturated. You cannot add anything in it. When relative humidity is 0%, air is said to be unsaturated. Yeah, okay? Dry. That's a better word. Dry. When relative humidity is 0, it's dry. So then we went through how relative humidity is related to humidity ratio in that equation. Okay? Then enthalpy, that's something very important as well. How do you write equation for enthalpy of air? So if you want to find enthalpy of air, any gas, okay? Let's say capital, not specific enthalpy. Let's say the total enthalpy H. Okay, so that's an equation. But before, how do we get that equation? I'm explaining you that. So if it was dry air, completely dry, there is no moisture in the air. So enthalpy of dry air will be equal to, normally what would you do? You do mass of air times specific heat capacity of air, Cp of air, times temperature of air. Right? That will give you enthalpy of air. Now, if air was moist, if that air had moisture in it, then you have to add, what do you need to add? Again, mass of dry air, still mass of dry air, times omega. What is omega? We just discussed. Specific humidity times HFG of water vapor. Why? Because moisture is in vapor form, and that water vapor will have that much amount of thermal energy in it, which is the latent heat of vaporization. Now what happens here? What's the unit of humidity ratio or specific humidity? What's the unit? Kilograms of water divided by kilograms of dry air. That is the unit. What's the unit of, these are mass, total mass. So that's kilograms of dry air. And what's the unit of HFG? Kilojoules every kilogram of water. So what do you end up getting? That kilogram of air cancels with that kilogram of air. That kilogram of water cancels with that kilogram of water, you end up getting that term as kilojoules. Similarly, in there, we have got kilograms of dry air times kilojoules every kilogram of dry air times kelvins, and that's in kelvins. So Kelvin cancels, dry air cancels, you end up getting that also as kilojoules. So enthalpy is of a moist air, okay? Enthalpy of moist air is equal to enthalpy of dry air plus enthalpy that is contributed due to water vapor or moisture within the air. Is that clear? Now the most difficult part is to estimate mass of water vapor. It's almost impossible to estimate the mass of water vapor. But what we can estimate is the total mass of air. Now, these equations in real world application, what you would be doing or how you would be using is you would have some kind of an air sensor, flow sensor, and you would know how much amount of air is being added to this room or to this building, how much air is being handled, how many kilograms or how many meter cubes of air every minute is flowing or every hour is flowing. Can you tell me a way to estimate the flow rate of air? Simple way of estimating, measuring flow rate of air. We're talking about big ducts. The ducts inside these false ceilings must be at least 600 millimeter diameter, carrying air through them. How do you measure the flow rate of air? Nothing to do with this particular course, but it's one of the fundamental things that you should know from fluids, first year or second year fluids. You must have, I'm very sure you must have done that. How would you estimate air flow rate? What device would you use? Have you heard of pitot tubes? Pitot tube manometers or digital pitot tubes these days can measure the velocity of air. Once you know the velocity, you know the cross-sectional area of the drum, whether this is a square duct, rectangular, or circular. You know the area times velocity, average velocity will give you the volume flow rate of air. You know the temperature, you can find the mass flow rate of air, knowing the density. So getting mass flow rate of air is easy. Mass flow rate of air, you can measure it, but to measure mass flow rate of water vapor, what would you do? Equals omega times mass flow rate of air. Okay, that will give you mass flow rate of water vapor. Now, how do you estimate omega? Knowing dry bulb and wet bulb temperature, we can estimate omega, and we're going to solve some problems that will help you understand. Because one question is definitely going to be based on all these equations that you will have to use, and I'll try to make it as simple as possible. Very similar to the questions from tutorials. Okay, but you should be able to solve at least those problems from tutorials. We won't solve it right now, but in a few minutes. Okay. So we've gone through that. Now, next question for you. Dew point temperature is saturation temperature of water corresponding to vapor pressure. Is it true or false? What is meant by dew point temperature? Or just the term dew point? What's meant by dew? Or the word dew? Everyone knows what's meant by dew? Dew drops, condensate that you get from the air. So, what do you think? What do you guess that dew point temperature means? The temperature at which moisture will start condensing from the air. Temperature at which we will get dew drops. Okay, and that's correct. But then, tell me if that statement is true or false. Dew point temperature is saturation temperature of water corresponding to vapor pressure. Now, what is meant by vapor pressure? That's the partial pressure of water vapor in the air. And if I go back one slide, not back, next, one slide. On the temperature entropy or temperature enthalpy diagram, we can draw it whichever way we want. That will be the vapor pressure. Total pressure is different. Let's say T is the total pressure of the air in this room, which is equal to partial pressure of air plus partial pressure of water vapor. We are treating air as a single species for now. We know air is made out of a number of different gases. Each gas will contribute to the pressure of the air. But for now we are saying, okay, it's a single species. Dry air is one thing and moisture is another thing. There are two components within the moist air, dry air and moisture. Partial pressure of moisture, PV, and partial pressure of dry air, PA. What we are drawing here is just the partial pressure of water vapor or moisture. Now, if we go down, if you start cooling down air, so let's say air in this room or air outside, if you start cooling down, at what point or what temperature you would start getting moisture condensed? Have you seen condensate forming in real world? Can you give me a real world example? Maybe today or yesterday or last 1 week you might have experienced this. Yeah? Some was aircon, yeah. Maybe a lot more simpler example. Can you tell me? Yes. No? Can. Coke can. Right? A cold Coca-Cola or any cold drink can, you take it out of the fridge or the machine and leave it on the table. Not here, because this air is quite dry now, but outside, what's going to happen? Moisture, you'll get a lot of moisture around it. It's not coming out of the can, out of the bottle, it's coming out from the air. Not sweat. Sweat is coming in from the inside out. Whereas the moisture which gets collected around that bottle or can is from outside. And when does that happen? When the temperature of the air now, not of the can, drops and reaches that point, which is saturation temperature. That superheated region, you start cooling down, and that point, if you continue to cool, water will start condensing, vapor will start condensing. Okay? So, answer to that question is, yes, that's true. Dew point temperature is equal to the saturation temperature at the given vapor pressure. Okay? That's true. We'll skip that part. Wet bulb temperature, I've already shown you that. So that's the difference. I was explaining earlier. A thermometer, and the bulb of the thermometer is covered with some kind of a wick. Wick means like a cloth or maybe a tissue paper, which is constantly supplied with liquid water. And you can get these days, it's very difficult to find these, but as an antique, you might find in an antique shop. These are sling psychometers. Two thermometers, one is covered with a wick, you have to add a few drops of water, other is open, and what you do, you hold the handle and literally swing it around. And the engineers used to do that, walk around, okay, wet bulb is this, dry bulb is this, get that chart, big chart, and start reading how much is the moisture inside the air. And let's do a quick exercise. So if dry bulb temperature was, let's say 30 degrees Celsius and wet bulb was 25 degrees Celsius, dry bulb 30 degrees Celsius. Wet bulb, 25 degrees Celsius. How much is omega? How much is relative humidity, RH? Plot from this chart. So let's start reading it. That x-axis is showing drawable temperature. Okay, I'm going to zoom in a second. And your wet bulb temperatures are these. So saturation temperatures, so 10, 15, 20, 25. And we are dealing with 30 drawable, which is there. Okay, 30 and 25, which is that line there. So 30 going up and 25 right at that point where they intersect each other. So mark off a little bit, and that was this thing. Sorry. Am I reading it right? Yeah, that point. So corresponding to that, so 15, 16, 17, 18, there's 18 grams of water vapor in 1 kilogram of dry air. So your omega is 18 grams of water every kilogram of dry air. Okay, and relative humidity is that point. These are relative humidity curves. You see here, relative humidity 10%, 15, 20, and so on. Now our point was somewhere there, which is around 70, 68 or 70%. Somewhere between 65 to 70. I'm just writing approximately 65% to 70%. Is that clear? How we read? Now, reading these graphs is one thing, but what I want you to be able to do is not just read them, those graphs, but calculate all these properties using equations. Why? Because those graphs are limited to a specific pressure. So for example, this graph is only, or can only be used if the total pressure, or the atmospheric pressure, was equal to 760 millimeters of mercury, which is 101.325 for that particular pressure. If the pressure was 101.5, 101.8, or 100.9, cannot use that graph, or you should not use that graph. You can still use that. Not, I can't say cannot use that, but it will give you a wrong answer. Small error in there. Further away you go from the pressure of the chart as compared to the actual pressure, more error it will accumulate or add. Is that clear? So, if in the test or in the real world, if you're facing a scenario where the pressure of atmospheric pressure that you're measuring is not exactly standard atmospheric, then avoid using graph. Better use equation. Okay. So, if we have a small Excel spreadsheet ready or a MATLAB script ready, you can easily type in whatever numbers you want, and it will give you the right answer. Okay. How many of you know how to make Android apps or OS apps? Anyone has explored? Yeah. Maybe you can make one of the apps using these basic equations and put it on the Play Store. I don't know who will buy it, but as just a fun activity. Maybe each one of you should try making an app. Just for your own sake. I mean, once you have these tools, and if you end up working in HVAC industry, that will all, if you find a job in a certain industry, make apps which are useful for your own job. As I said to you earlier, Yesterday I was giving an example. Your boss comes and says, complete this, and you've got everything ready, but all the models are ready mathematically, computer models, and it might take you 5 minutes to do the whole thing, but you were going to say to your boss, give the real time. Like if you do everything from the scratch, it might take 4 hours, half a day. He's happy. Okay? So let's continue. So this is how you read charts. Now, and this is the most important bit, and then once we finish that, we can take a break and come back and continue solving your assignment. Okay? This is the most important. Why do we need to study all these equations, and we should be able to manipulate the air. Okay? So my question to you is, the air outside today, which is hot and humid, if I say, okay, here's the air, hot and humid air, make it comfortable for human occupancy, for human use. First thing, what would you do? First thing, would you ask me a question? What is meant by human comfort? Now, question goes back to you. What do you think is human comfort? What temperature is comfortable for humans? 25, okay. 16? What about moisture content? What about relative humidity? How much relative humidity is comfortable for humans? 100% relative humidity? 5% relative humidity? 55, 60? Okay, good. 60, 55, 60% is comfortable. If it's 5%, can you tell me where would you experience 5% or 10% relative humidity? Which parts in the world? Desert, maybe, yes. Where else? High mountains in Alps, snowy mountains, plenty of snow, and moisture cannot, because it's so cold, moisture all condenses. So it's very dry. Deserts is dry, and mountains, like snowy mountains, is dry. And where is very moist air? Singapore. Right? Tropics. I mean, Queensland in Australia, if you go to the northern part of Australia, very hot and humid. Most of the Southeast Asia is hot and humid. Tropics. All tropics are hot and humid. So, okay. So question back. How are you going to manipulate that air and supply comfortable air which is at 20 degrees, let's say, and 60% relative humidity? What are you going to do? So outside, let's say today is at 32, 33 degrees Celsius temperature, and the relative humidity must be around 80%. So 80% relative humidity, temperature of the air is 30 degrees. We want to reduce it to 20 degrees and relative humidity of 60%. So I'm going to show you the psychometric chart, and we are going to assume for now pressure is exactly that pressure, atmospheric pressure outside. Let's do a quick mental exercise. So air is at 30 degrees, you want to cool it, right? Definitely we want to cool it down to 20. So what are you going to do to cool it? How would you cool air? What machine are you going to use? What process are you going to use? Heat exchanger, okay. What are you going to do with the heat exchanger? I mean, these are simple questions, so there's nothing complicated. I want you to build the story. With heat exchanger, what? And extract the heat. Okay, with the heat exchanger, extract the heat and dump. So where do you want to dump it? Outside is 30. Using what? Compressor, okay. Using a heat pump or a refrigeration system. So use a refrigeration to remove the heat from the air, dump it to the outside. And the way you can dump it is only if that heat is at higher temperature. Only then heat can transfer to the 30 degrees Celsius. So with the compressor, you're increasing the temperature of that heat to 50 or 60, and then you can dump it to that one. Okay. So you've cooled down the air to 20 degrees. Initially, relative humidity was 80%. Now, can you tell me what's going to happen to the relative humidity if you've just cooled down the air to 20 degrees? Will the relative humidity go down or go up? Let's find out on the chart. Now, 30 degrees and 20 degrees. Which temperatures were there? Dry bulb or wet bulb? Dry bulb, that's correct. 30 degrees was dry bulb, we were just measuring with a dry bulb, 20 degrees is also dry bulb. So, everyone can see that? So, originally we were at 30 degrees and 80% relative humidity. So, that curve somewhere up there. Now, from there, we have cooled down from that point where my cursor is, you have cooled down to 20 degrees. What's going to happen if you go that direction? Let's not even worry about 20 degrees. Let's say from 30 you have cooled it down to 28, 2 degrees cooling. What's going to happen to the relative humidity? Increase. From 80 is gone to 90 already. From there, if you move up to there, it's 190. You move further, you cool it down to 25 degrees, relative humidity is already 100%. Now what's going to happen when the temperature of the air reaches 25 degrees? You have cooled down that air which was at 30 and 80% relative humidity, you have cooled it down to 25. Relative humidity has increased to 100%. Now you continue to cool it to 24. That's what's going to happen. 1 degree cooler, condensation will start. You will get droplets, dewdrops. You cool it further and go to 20 degrees, you will get lots of condensation. But what will be its relative humidity? So you reach to 20. So what's going to happen? You will first hit. The process will look like it goes from there, horizontal, and then continue following that curve and reaches 20. And that's where we are at the moment. We have cooled down the air from 30 to 25. In turn, we have removed some moisture. So originally there was some moisture, a certain amount of moisture. We have cooled it down and removed some of the moisture from the air just by cooling it. But our target is not relative humidity of 100%. We want relative humidity of 60%. So what are you going to do next? How? Dehumidify how?
Desiccant.
Okay, one of your classmates is saying use desiccants. We could use desiccants. Perfect. What else can be done? The only trick with desiccants is though, very difficult to control how much you can remove. You might end up getting a very dry air. So control, very difficult with desiccants.
Air dry.
We want to go to that curve. So we are here, but we want to be here. Heat it. If you heat it,
The
temperature goes 25. I mean that's a good idea. I'm not saying I don't support that idea. I support that idea. But do you think you need one more step before heating? Because if you just heat it, it goes to 25. Can you cool it further and then heat it to 20? So you continue going further. So let's look at 20 degrees where it crosses 60%. 20 and that's 60% there. So if you cool it down up to that point and then heat it, we can go to 20 degrees, 60%. So you cannot just cool it to 20, you have to cool it down to about 14 or 13 degrees Celsius. So you cool the air from 30 to 14 or 13 and then heat it to get to the right temperature, and that's so precise. So although chemical desiccants are easy to use, less energy consumption, but they don't have control, precise control. Mechanical devices, and that's where you, mechanical engineers, we come into big play. This controls. Have you done automatic control? Or it's next semester, next year or next semester, maybe. Automatic control. This is what you do. You are learning things in this course. You have learned things in few other courses. Heat transfer. You're combining. By the time you graduate, you have enough knowledge to make a system operate, to make a algorithm, kind of a code, which will control an entire system. When to turn on, off, on, off. Basically, it's on-off switching. Switching a heater, compressor, between refrigeration, cooling. So you cool, stop. You're going to write a code saying, once the temperature of air reaches 14, shut off, shut the cooling, turn on the heater. Makes sense logically? I mean, and that was a simple logic, but there will be a lot more complicated logic. Why? Because you have to write a code which also needs to take care of the end user interface, like a panel. I think we have somewhere panel there at the back, that corner. He's sleeping. That corner, is that a air conditioning panel, right? You can set the temperature there. It's getting very cold. I can see a lot of you are putting hoodies on. You want to heat it up maybe? 23 right now. So if we go and change that, how is the system going to react to that? Someone has written some code that user interface, how to take that user input and rewrite the code. Kind of. It's not going to be cool it down to 14 or cool it down to 13. That 13 or 14 will be a variable. That will be the user input variable, end user input variable. Make sense? Good. So we can manipulate basically air. You can heat, cool, humidify, dehumidify. In case of deserts or places where air is very dry and you want to add moisture, you can add moisture, and the simplest way of adding moisture is having a pool of water, you heat it up and let it evaporate. That's the simplest way to, or another simple way to add moisture will be spray water into the air, make very fine mist spray, and that evaporates this. Okay, what's the time? Maybe we can solve one question and then go for a break. Okay. Has Raj solved this problem? Don't remember? Maybe not. Let's solve it again. Even if it's solved, let's solve it again because it will help. So a 5 meter by 5 meter by 3 meter room, maybe something like this, or a little smaller, contains air at 25 degrees Celsius and 100 kPa pressure at a relative humidity of 75%. Determine partial pressure of water vapor in the air, specific humidity, enthalpy per unit mass of dry air, and water vapor. What I want you to do now is go to week 10 folder, and so yesterday I showed you I've added some extra notes under July 7th section. There's a formula sheet. So let's open that formula sheet, because for last piece of assessment you only have access to that formula sheet. And let's use that formula sheet to solve this problem. We'll show you where it is. week 10 lectorial material from 7 July.